Okay, we're going to look at doing some operations on matrices. So we can add, subtract, multiply, and kind of divide matrices. And so when you add and subtract, so looking at the first 1, 2, and 3 here, these guys are going to behave similar to what you would expect. Now, one other thing to kind of notice is that these matrices all look a little different. Matrix A, we actually say, is a 2 by 3 matrix, 2 rows by 3 columns. B is a 3 by 2 matrix, 3 rows by 2 columns. And matrix C we have, again, is another 3 by 2, 3 rows by 2 columns. And so what happens if you want to add matrices, the first thing is that they have to be the same size, the same number of rows and the same number of columns. So if you look at adding A and B, we actually can't. So it's not possible because they are different sizes. When we want to add matrices B plus C, those ones we can because they are the same size. So let me go back. A plus B, they must be the same size. So here that's not possible. You cannot add them. But when you look at B plus C, they are the same size. And so in order to add, you add each entry. And so what that means is matrix B plus C, which is a brand new matrix, is found by adding the first row and column with the first row and column. So we're going to take -8 plus 4, which will become a -4. Then we're going to add 0 plus -5, which will be -5. And then we're going to take 1 plus 12, which will be 13. We're going to take the 5 plus the 3, which will make 8. -4 plus -2, which will be -6. And then 1/2 plus 2, 1/2 plus 2, that's going to be 2.5. I'll write it as a decimal. So that is my new matrix B plus C. So to find C minus B, again, we need to make sure that they are the same size, which they are. And this time we're going to subtract the entries. Or you can think about it that you're going to put a negative to every entry in matrix B. So what that could look like, so matrix C, I'm going to rewrite matrix C down here. We have 4, -5, 12, 3, -2, 2. So instead of writing subtract, I'm going to say, okay, I'm going to add, but I'm going to take a negative to everything in matrix B. So that'll be a +8, 0, -1, -5, 4, and -1/2. And that's just a nice thing to do so that way you don't forget to subtract any of them as you go to combine. So again, entry by entry, 4 plus 8 will make 12, -5 plus 0 is -5, 12 plus -1 is 11, 3 plus -5 is -2, -2 plus 4 is 2, and then 2 plus -1/2, well, that's just going to be 1.5 or 1.5. So we just found matrix C minus B. Now to find matrix B plus 2C, we are going to add entries, but we're looking at double whatever C is. So I can write out matrix B first. So matrix B, again, was -8, 0, 1, 5, -4, and 1/2. Just double checking that. And so we're going to add to that double C. So double C means 2 times every entry in C. So that would become 4 times the 2 would be an 8, a -10, 24, 6, -4, and 4. Which will equal, again, if we go term by term, it'll become a 0, or entry by entry, we get 0. We'll get a -10. We'll get 1 and 24, that'll make 25. 5 and 6 make 11. -4, that makes -8, and 1/2 with 4 makes 4.5 or 4.5. Now multiplication is a little bit different, and it's good if you in your head if you keep in mind, okay, multiplication is a little weird. So in order to multiply A times B, it's not that they have to be the same size, but they have to have a little matchup going on. And what I mean is this. Matrix A was 3, 4, -7, 9, 2, 0, And matrix B is -8, 0, 1, 5, -4, and 1/2. And so what happens with multiplication is we actually will multiply term by term, but a little differently. We need the row and the column of the second matrix to be the same size. So this was 2 by 3, and this is 3 by 2. So you need to make sure that the number of columns equals the number of rows of your other matrix. And so what ends up happening is you take those and multiply like 3 times -8, and you're going to do 4 times 1, and you're going to do -7 times that -4, but you're going to add those up, and that's going to be your first entry. So we took row 1, column 1, and that's going to be our first entry right here. So then we're going to do that again, still with that same row. So we're going to have an entry in our first row still, but we're going to do it times our second column, which gives us another entry over here. So we're going to do 3, make it a little bigger, 3 times 0 plus 4 times the 5 plus -7 times the 1/2. And then we're going to start that process again, but as we move down to the second row, we're going to be at the second row of our new matrix, and it's the first column. So we'll do 9 times -8 plus 2 times 1 plus 0 times -4. Then we're going to take still second row, so we're going to still be in the second row, and second column though this time. So we'll do 9 times 0 plus 2 times 5 plus 0 times 1/2. So what that ends up being is, let's see, our first entry will be -24 plus 4 plus 28. That's going to be 8. And then our second entry will be 0 plus 20 minus 7/2, that's 3.5. So 20 minus 3.5 will be 16.5. And then our second row, we're going to get -72 plus 2 plus 0, so we'll have -70. And last we'll have a 0 plus a 10 plus a 0, so we'll get 10. So this is my matrix A times B. Now if I scroll over to, so let's look at the B times A. So B times A would be -8, 0, 1, 5, -4, 1/2. So this is a 3 by 2 matrix times 3, 4, -7, 9, 2, 0, a 2 by 3 matrix. Now we can still do this multiplication. It's going to end up a little bit different from the last one. It's not commutative, which means you can't go back and forth and get the same answer like you can with regular numbers. Regular numbers, 3 times 2 is the same as 2 times 3, but that's not the case with matrices. But since these match each other, we know we can do our multiplication. So remember how this works. We're going to take the row times the column. And again, we know that works because every guy has somebody to multiply with. So our first entry, because we're in row 1, column 1, and that's going to be where our first entry is, -8 times 3 plus 9 times 0. Then we're going to take, again, first row, but second column, and that will be a -8 times 4 plus 0 times 2. Then we're going to do still first row, so we're still in the first row of our answer here, but times our third column. So -8 times -7 plus 0 times 0. Then we're going to go through that process for each row in our first matrix B. So let's start here. We're going to take that 1, 5 times 3, 9. So 1 times 3 plus 5 times 9. Then we're going to take 1, 5 times the 4, 2. So 1 times the 4 plus 5 times the 2. And then again, last one, this is our, again, we're in row 2 times our third column. So our entry will be in that spot as well. So 1 times -7 plus 5 times 0. And then we go moving on to our third row times our first column. So that will be a -4 times 3 plus 1/2 times 9. Then we're going to do, again, that third row times our second column. That'll be negative 4 times 4 plus 1/2 times 2. And then the last one, again, bottom row, third column, that'll be negative 4 times negative 7 plus 1/2 times 0. And then we need to simplify that. So I know I'm running out of room here. This is going to equal, so let's see. This will be negative 24 plus 0, so we have negative 24. Negative 32 plus 0, so we have negative 32. 56 plus 0, so we have 56. 3 plus 45, we're going to get a 48. 4 plus 10, we're going to have 14. Negative 7 plus 0, we're at negative 7. For the bottom, we have negative 12 plus 9/2 is 4.5. So that's going to be negative 7.5 here. Negative 16 plus half of 2 is 1, so we'll get a negative 15 there. 28 plus 0, we get 28. So this is my BA matrix. One other thing to notice is that we were looking at getting these guys to match each other, but the 3 and the 3 tells you the size of my new matrix. It's a 3 by 3 matrix. All right, one more, BC. So matrix B was 3 by 2, and matrix C was also a 3 by 2, so we actually can't do that one. We can't multiply the BC. Okay, so we've looked at adding, subtracting, and multiplying matrices, and so just a thing to point out, we have an additive identity. So the additive identity is what number you can add to a matrix that will make you still have that same matrix. So in just notation, it's A plus 0 equals A, but the A we're talking about is the 0 matrix. So if I have like A, B, C, D, I need to think about what I can add that would still get me the A, B, C, D. Now, because we add by looking at just the individual entries, this would have to be a 0. This would have to be a 0, 0, and 0. So really we're talking about our 0 matrix being equal to a matrix filled with zeros. So this is going to be the additive identity. The multiplicative identity is what you can multiply a matrix by, A, B, C, D. That will still give you the matrix A, B, C, D. And this one's going to look a little bit different because when we multiply, it's not entry by entry. It's row times the column, row times the column. So it's actually 1, 0, 0, 1. And this is the identity matrix. Sometimes it's denoted with an I for identity. In this case, it would have a little 2 because it's a 2 by 2 matrix. If it was a 3 by 3, it would be I with a little 3 next to it. So let's check how that multiplication would work. So we take the first row times the first column. That gives me my first entry. A times 1 plus B times 0. Then we take that first row times the second column, and that will be A times 0 plus B times 1. Then we take CD times that first column. That will be C times 1 plus D times 0. And then lastly, again, we're in the second row, second column, so that's where my entry is going to go. We're going to have 0 times C plus D times 1. And you can see we're going to get just A here, just B here, just C, and just D like we needed. So the identity matrix works the way we need it to. So the next part that we have is our inverses. We have an additive inverse, and really that's saying what can I add to matrix A, B, C, D that gets me that 0 matrix. And that's going to be really a matrix just having opposite signs because, again, we add entry by entry. For multiplication, it's not going to be as obvious, and it's actually, again, we're taking this matrix A. When we multiply by its inverse, which will denote it with a little -1 like this means inverse, we want to get the identity. And so here, if we have matrix A, B, C, D, we're saying we want to multiply by something that, in this case, because it's a a 2 by 2, we would end up with the 2 by 2 identity. So we need to figure out what this thing is that we can multiply by. And so we're going to derive the formula for it down here. And the way that it works, we don't know what those entries are. I'm going to call them, let's see. Let's write this as x1, x2, x3, and x4. So what we're saying is that AB, that row, times that column. So AX1 plus BX3, we need that to equal 1. We're going to kind of continue on. We need A times x2 plus B times x4 to equal 0. We also need C times x1 plus D times x3 to equal 0. And lastly, we need C times x2 plus D times x4 to equal 1. And so what that looks like, we actually have two little systems here. We have a system that is with an x1, x3, and we have a system that has x2 and x4. So let's look at just one of these to get an idea of how this should work out. So if I'm looking at the a sub x1 plus b x3 equal to 1, and the other one cx1 plus dx3 equal to 0. If I want to solve for, let's say, x1, that means I'd want to eliminate my x3. So this would need to multiply by, well, really the opposite of the other guy. So negative d here. And this one is going to multiply by negative, no, not negative, just positive b. And both sides. So the top becomes negative AD minus DB equals negative D, and sorry, x1 and x3. The bottom equation becomes BC x1 plus BD x3 equal to 0. So when we combine these together, you'll see the x3's cancel. We're going to have negative AD x1 plus BC x1 equal to negative D. And if I factor out the x1, that looks like negative AD plus BC equals negative D. So to solve for x1, I'll divide by that negative D plus BC, divide by that negative AD plus BC. We get x equals negative D over AD, negative AD plus BC. Or we could rewrite this if we kind of move that negative, take that negative out. It will be D over AD minus BC. I just kind of factored the negative out of this and reduced. So to find the x1, go back to what we were talking about, the x1 is going to be found that way. Now if we do this similarly for x3, x2, and x4, we end up that this x1, x2, x3, x4 is really D over the AD minus BC. We already got that. Then it'll be negative B over AD minus BC, negative C over AD minus BC, and A over AD minus BC. But we could actually rewrite that as, like, take out that 1 over AD minus BC, and we'll have D, negative B, negative C, A. And this is, again, another form to write for a 2 by 2 inverse, given that the matrix was A, B, C, D. So it might be nice here to see an example. I kind of wrote this a little big here. But if we have a matrix, let's see, for example, 1, 2, 3, 4. If we want to find the inverse of this, I'm going to call this matrix A. We want to find the matrix A inverse. So all we really need to do, if we look at this little formula here, they're switching some letters around. So for this A inverse that I wrote an equation for, it comes from this matrix being my matrix A. So if you pay attention right here, you can see they flip-flop A and D, and then they just negated the B and the C. So let's do that here. I'm going to flip-flop A and D, so that's going to be 4 and 1 flip-flop. And then the 2 and the 3 become negative. And so I need this times that 1 over AD minus BC. Well, AD is just that first diagonal, 1 times 4, minus the BC is the other diagonal. And we're going to actually see a name for this next time, that this is actually, this bottom part, is called the determinant of a matrix. So we have this is 1 over 4 minus 6 times 4, negative 2, negative 3, 1. This is 1 over negative 2, so negative 1/2 times that 4, negative 2, negative 3, 1, which becomes, if I multiply that in, we're going to get a negative 2, a positive 1, positive 3/2, and negative 1/2. So this is what we're going to say is our inverse matrix. And that's just using the formula. So again, all I did was plug in to this formula that I showed you we could come up with.